Thank you, Manuel, and thanks for the invitation, and thank you all for being here today. Some of you might recognize me because I hosted this also in the past year, so maybe if you're a frequent attendee, you might recognize me. Yeah, so as you might know, for this series, we have four different topics that we sort of cover, and actually my talk is a bit of a mixture between the two, between innovations in light exposure or behavior logging, which will cover the first half of the talk today. And then we have a second half where I will be talking about an experiment that sort of investigates also seasonal rhythms and rhythms that are obviously not 24 hours. Right, so let me start with the first block. And I brought a bit of a provocative quote here. This is from a marketing campaign, and obviously you can see that the reasons why they might want children to go outside if you realize that the source is Persil or Unilever. But I think it's an interesting quote because they basically surveyed parents about how many hours their children spend outside. And it's quite a big study and actually, or survey, and actually it matches quite of the other data that we have on this. And as children progress in their school timing, so in like how long they spend basically in the school system, their outdoor time reduces over the years. And so, yeah, it says here children spend almost the same amount of time outdoors as prison inmates. And this is indeed kind of comparable. So if we look at data from the US, where prison inmates spend about 2 hours a day outside, or in Germany, it's about 1 to 2 hours. This is exactly what we see in maybe not very young children, but sort of maybe around the age of 10 and onwards. So really, it's not that not a lot really, and I think it's quite worrying as well. And so this is the daytime thing, but then also we have a change in how our nights look like, right? So we used to be here on this left side where there was no light pollution at night, and now with the recent years or since electrification, we moved more towards what we see here on the other extreme, where there's a lot of light pollution and we cannot see the sky anymore. And indeed, with the estimated light pollution growth of about 6% a year, it's sort of predicted that all of the developed world may lose its dark skies by the end of the 21st century. Yeah, so we sort of end up with a situation that some people have already covered here in this series, but just to highlight again that most of us spend a lot of time indoors and during the day with very dim lighting conditions, and at night when it's supposed to be dark, we expose ourselves to screens or other technology that emits light. And so we moved to more dim days and lit nights. And now I'm just gonna quickly go through why this matters, because I think we've heard of this many times before, but as you know, light is not just for vision, but it also modulates non-visual physiological processes. And this is mediated, so the visual pathway is mediated by the rod and cones, but the non-visual pathway, the non-image forming pathway is mediated mainly by the iPRGC cells. And these in turn then downstream affect the peripheral clocks that are affected by this central circadian pacemaker. And this is why the light is so important. And yeah, this is just to highlight again that the synchronization is important for our rhythms. It also influences or modulates the sleep-wake cycles, hormones, mood, alertness, metabolic function. Also, the pattern of light that we expose ourselves to is important. So we have a spectral diet that we should consider in studies. And obviously, excessive light exposure at night and dim daylight is sort of linked with negative health outcomes. And for example, light at night, or ALAN, is a potential factor for cancer development. And mesoland rhythms are, let's put it just, they're not good for you. They're associated with a range of negative outcomes. So also one aspect that we've covered partly in the seminar series also was that too little light in combination with near work might lead to myopia, which is especially in Asia is a growing health concern, but there is also some prevalence here in Europe. It's not just that this is an Asian thing that we should look at. So overall, I think effects are not integrated into routine public or even personal health practices. And yeah, I think this is something that we should look at. And yeah, I mean, this is partly also, the reason for this is partly also because we haven't had much of a recommendation, right? So it was quite unclear on what are you supposed to do, except that, okay, get more bright days and darker nights. And so there are some recommendations out now for healthy light exposure, which I summarized here. So basically during daytime when you're indoor, you should at least get 250 lux melanoptic EDI. And primarily this is supposed to be done through daylight. And if you use electric light, it should mimic the natural daylight. In the evening, 3 hours before bedtime, it shouldn't be more than 10 lux. And the spectrum should be depleted in short wavelengths. And at night, it should just be as dark as possible. So yeah, bright days and dark nights, just as it used to be. But really, I mean, one complication here is that who knows how much this is? You know, if you go back, who knows how much 250 lux or 10 lux? Like even when I study this, I wouldn't be able to tell exactly. So how should a normal person know about this? So this is definitely a limitation that we have to tackle. And yeah, so to sort of combine the light with the sleep part, I sort of want to develop some prevention strategies in the long term. And I think what we need to do this is we need to really understand intra-individual variability and understand its relevance in healthy people, and identify individual sleep determinants. And that's obviously light, but it's also, you know, other biological, environmental, personal, or also socioeconomic factors in the real world, and see what their magnitude is on these specific sleep determinants. And then only then, if we really understand this really complex picture, I think we can provide some very, very nice personalized prevention programs, also maybe real-time interventions, because I think then they are so tailored that this will increase the adherence and long-term benefit. And I think right now we're not really there yet. It's quite generalized at the moment, but also because it's so complicated to, you know, factor in all these determinants that we are experiencing in the real world. And so I think my research gap that I think of is that we need to identify these factors. And parts of this basically comes back to methodology. How do we even measure a personal light exposure? Which metrics should we use? I've already alluded to this a little bit. We also need to, do this research in the real world, I think, even though it becomes much more messy and complicated. But I think if we really want to get there, we sort of have to be brave and start doing this. And also I think framing light more as a behavior is something that we could consider. And I'm going to talk about this in the next slides. Yeah, and then just also sampling longitudinal data to really understand the variance within the person, because it seems to be that this variance is quite large, and also the differences between people is quite large. Okay, so let me first go into this idea that light exposure is a behavior. So we've come up with this Venn diagram, or we also call them bubbles, where we sort of try to understand and put this into a framework of how these different factors actually interact, and what are these factors even that influence how we interact with light, how we expose ourselves to light. And so we put location here as the outer bubble, because really you cannot change anything about the others. You're always in a location. So location really encompasses everything. It determines your photoperiods, your sunshine hours, the climate, temperature, and so on. And then, of course, within this culture, you develop different norms, festivities, or customs that are partly also related to the location, because you might have longer photoperiods and then influence your culture, how you develop around this. Then you also have the built environment. Of course, we spend most of our times these days indoors. So the window, the glazing, the proximity to it, the architecture, lighting design, all play a role in how we can expose ourselves to daylight or light in general, and how we interact with it. And then, of course, there are all these individual behaviors that are shaped by all of these other bubbles. But of course, you are still an individual So not every individual who experienced the same built environment, culture, or location would act similarly. So of course, there's this psychology, this individual behavior, and this, is, for example, shown in individual preferences or lifestyle choices. And just to give you some examples here, like this is a typical sunny day, I would say, in London, where people really expose themselves to the rare sunshine, whereas in other countries in Asia, people would hide if from the sun because of tanning reasons, for example. Also, architectural styles are different. Like here you'd have the typical balconies, whereas in Kerala you'd have more of, these kind of architectural features and so on. So it just shows you a visualization of this framework. And I'm gonna play you some associations that people reported to us when we interviewed them. So this was part of a summer school, and here we hear associations with daylight and darkness. And I think it really nicely summarizes this idea how different it is for each individual person, but I think some of it is also cultural, for example.
Sun, warmth.
Relaxation.
Summer, grateful. Heat, shiny. Burning, sunscreen. Seeing.
Yeah, spectrum.
And clearly the last person was someone who knows about the spectrum, otherwise they wouldn't have said that. So I think it's quite funny. And now we listen to the dark associations with darkness.
Stars,
Northern lights.
sleep. Winter, peaceful. Sad,
Atmospheric.
calm. Tired, unable to see.
Exactly. Okay. So
Sun,
Oops.
stars.
Go to the next one. Okay. So what we can also recognize is that when you feature all of these in, is that obviously no one is the mean, right? So you'd have different light exposure profiles for individuals. And this is something that we just visualized here. So on the x-axis, you have the time of day, and then the y-axis, the melanopic EDI. So yeah, light coming in. And basically you can have all these different metrics that summarize aspects of this profile. And I just want to highlight here that really these are two individuals, the blue one and the yellow one. And you can clearly see that this yellow profile basically gets much more light at night, whereas the blue profile is just earlier with the light exposure, for example. So these are two metrics you can look at. But basically, yeah, since no one is the mean, it's quite interesting to look at how are the differences, and are there differences in different cultures as well. And this is something we looked at in this study here. So here we compared participants at two different sites, one in Basel, which you can see here, and in Switzerland, and one in Kuala Lumpur in Malaysia. And we had participants that wore a light logger at the chest for 4 weeks, the SPECI device. And they also filled out the sleep quality questionnaire and light exposure behavior questionnaire. And we wanted to understand some differences between them. And of course, you can already see the location is different. So we obviously had to account for the photo period duration change. That is what difference between these two sites. While Kuala Lumpur doesn't have any variation photo period, Basel obviously has across the year. And what was what were our findings? So compared to Switzerland, or the other way around, sorry. So Switzerland actually showed, this is in yellow here, showed twice the duration in daylight levels of per hour of daylight. So meaning that these participants in Switzerland, they just had longer duration in daylight. They also had brighter days, but they had about 1.5 hours later bright light exposure in the afternoon. But if you look at the differences, actually their evenings were dimmer, and their daytime exposure was brighter than the Malaysian participants. So if we look at the ground mean here, you can see that visualized again. So for example, here's the 250 lux line, And there already you can see that this is not reached by the overall population, whereas in Switzerland it is. And you can also see that this shift towards dark hours is shorter in Switzerland than it is in Malaysia in our data set. So I think apart from the fact that we have individual differences, there might be some cultural differences in exposure as well that we can see in these grand averages. And so when we talk about recommendations, we should factor in these potential differences as well. And now that was more of an objective part, but you can also ask about their behavior, which is more like how they interact with the light. So how is the screen used, for example? How much, do they use screens or phones? Do they use any filters, blue light filters, etc.? And so for this, we use the light exposure behavior assessment, the LEBA questionnaire. And there we didn't see any overall differences between Malaysia and Switzerland. So that was quite interesting. And also these items were stable over time. And they did correlate with the objective light exposure that we measured with the light loggers. But this was only in Switzerland with a magnitude of mid magnitude and also in the expected directions, but again, only in Switzerland. So here we see again, there might be some cultural differences, maybe also how the questionnaire is designed. But in any case, it seems to be that we really need to focus on these differences as well. And future work might be able to understand if questionnaires can replace light loggers. And I think another speaker in this seminar series, Altuk, has already talked a little bit about this. So if you're interested in this as well, you can also check out the recording on YouTube, because obviously we recorded this. So when we move on to, again, more the objective part of the light measurement, the question obviously always comes up, where can we measure personal light exposure? And so here in this study, we basically compared theoretically, so people did not wear these devices, they filled out a questionnaire where they would hypothetically wear this device. And so we came across, or we draw different options here, and you can see the chest pin here on the left side, and then all these different options onto the glasses on the right side. And obviously the most relevant location physiologically would be at eye level, so that would be the glasses. And here you can see some examples of how these devices would look like. But of course, these are just examples. There are a few other loggers out there, but there are not too many devices that we can use that are on the market. So we asked them different questions because we were interested in how they perceive all these locations. And so the participants filled out, for example, how likely it is that they would wear this device. And you can already see that the chest pin, the wrist, and the neck positions are preferred. So you can see this here. So they are quite likely to be worn, whereas the head pin and the glasses are not very, very likely to be worn. And I think this is something that's quite obvious because it's much more disruptive in the face. Light loggers are also more likely worn at home. So here we ask different, so the likelihood of wear ratings depending on the context, different settings basically. And of course, I think that's also quite clear if people feel more comfortable wearing it at home. But still, they were also, kind of happy to wear it in different settings. But I think it's a combination of what device it is and where is it worn. So this is something you can see here. Basically, especially the chest pin, the wrist, and the necklace positions were most likely worn across all contexts, whereas the others, as you can see here, it was quite unlikely that people would wear these devices. And this is unfortunate, obviously, because glasses are the ones that we want them to wear. But it's absolutely clear that this is super unfeasible especially for very long-term studies. This is something that I already pointed out. But just here, we also wanted to see how many hours you could imagine wearing the light logger during the day. And you can clearly see how it becomes less popular, or shorter when you go from chest pin to glasses. And I think something that was quite interesting is to what extent do you believe the light sensor would restrict your daily activities? And here it seems quite positive. I think I would have expected that people would be more negative about this, but it seems relatively positive. So this was about wearing positions, and I think it kind of leaves you with the idea that glasses are the best option, I guess, if we want to have valid data, but it's very unlikely that people would wear this long term. So this is something maybe you could consider for a short amount of period, but if you want to have very long-term studies, something around like wrist might be the better choice. Or even necklace, I think it didn't work out too bad in the study. And this is also an experience that I had in my study, which I will present later, that the necklace position was actually not too bad for the participants. They got used to it. They had to have a little period where they had to get used to it, but then eventually it worked out quite well for them. Except when they had to change seasons, or like the seasons changed and we went into winter, for example, and people would start wearing more coats and so on. They had to change their behavior in the sense that they had to remember putting things outside, putting the necklace outside so it wouldn't be occluded. Right. Another thing I think that's important when we talk about light loggers is that we have some sort of tool on how we compare these different loggers. And here, colleagues, and especially Johannes here, has developed a very nice web-based specification tool for wearable light loggers and optical radiation. And you can scan it here if you want to visit the website. I also shared the link here. And what is this? So basically it's open access, it's web-based, and it provides a structured framework for defining, comparing, and communicating device requirements. So it integrates expert-informed parameters like usability, fidelity, and data requirements. And the idea is that you can fill this out and then generate an exportable Word or PDF file that contains all these specifications, for example, for procurement reasons or documentation, or for example, if you want to go and ask a specific company if they can, or if their logger would fulfill all these requirements that you have listed in this document. And the aim overall is really to support this transparent and consistent specification sharing and harmonization in light exposure research, and that we just make sure that we can reproduce results and compare these loggers. I think it's quite important because they have different specifications, and if we change this and if we don't always use the same loggers, then these can obviously also impact our results. And this is just how the website looks like. So if you go there, you get some information, and then you can just start the specification, and that would lead you to this form here, and you just fill out all these things that are interested to you, or that you want to document. You are not you don't have to specify all these boxes, but it would help you. The more you put in, the more information you collect and can make it comparable, I guess. And and then you can click on create or download PDF, and it would give you the output. And some of the dimensions that we thought of was basically featuring around the long-term usability, so use cases, suggestions, and for short-term use, medium-term use, or long-term use, and then obviously the fidelity and accuracy part. Yeah. Okay. Now I wanna basically go on about what we are still missing apart from this logger specifications, and that we need a specific light logger that sort of combines all these different use cases, which is very hard. But there's some other research gaps and priorities in light exposure research that we identified in a paper that we recently published. I don't want to go through all of them, but just highlight a couple of them so we get an understanding of where do we still have to do our work. And so I think a very important one is this first one, the limited integration of non-visual effects of light into public health frameworks. So I think even with sleep, we're lagging behind, but I think there's more awareness about what's going on with sleep and how important sleep might be, but the light and the non-visual effects of light are really lagging behind. And I've already talked about the standardized measurement tools, so I'm just gonna quickly go over that, but apart from the tools itself, we also lack, I think, consistent exposure descriptors and exposure metrics. And really one big thing is that we don't have an agreement on what are our core outcome standards. And so in the end, if we don't know this, it's also very hard to define, this dose response evidence, or even do this evidence, because if everyone uses different outcomes, different metrics, it'll be very hard to come up with this. But only this, I think, will enable us to feed this into the public health framework. Okay, so with this, I'm gonna switch from this light exposure logging part and come and move forward to this clocks beyond 24 hours idea. And so we talked a lot about the light, but of course there are other sleep determinants that influence how we sleep. And this could be contextual and environmental determinants. And some things that I'm interested in is basically the seasonality part, but also some day-to-day variance and the magnitude of these different determinants and the individual variability. I talked about this at the beginning already. And so one study that I did was the Ecology of Human Sleep cohort study, the EcoSleep study. And here we investigated how people sleep and a lot of other factors for 1 year, so 12 months. And we had a small cohort, but it was almost like a deep phenotyping study. And they were healthy, 18 to 35 years. And we measured a range of things, as you can see here, like logging, glucose sensor measurements, so continuous glucose measurements, actimetry, also EEG, saliva sampling, and skin temperature. So these are just a few of the measures that we did. And here it's just summarized again how we did this. So we basically had for 12 months this continuous measurements. And apart from the 3 that I already mentioned here, we also have placed a bedroom temperature sensor in the bedroom that measured temperature, humidity, and air pressure. And apart from these continuous measurements, then we had also a measurement session per month. And this was basically, or each session consisted of 3 days, which we can see in this slide now. So this would span from Monday to Tuesday and Tuesday to Wednesday. And most importantly now for this talk, I'm going to focus on the EEG night. So every night from Monday to Tuesday, participants would wear an EEG device at home, and Tuesday to Wednesday as well. And so here I'm interested in the sleep architecture and how this changed across the year. Additionally, we also collected monthly questionnaires, a lot of them. Here you can see all the different ones, and the ones in red is the ones that I will talk about now in the remaining time. So chronotype questionnaire, sleep quality index, sleepiness, and fatigue scale. Right, so how did we approach this seasonality aspect? So first, I have a very crude, categorization of season spanning from spring, summer, autumn, and winter, as defined here. And the reference category was always the winter. So we compared everything to winter. But this is, of course, categorized. So I also wanted to see if there is more of a variable that, like photoperiod, that's numeric and not categorized. And for this, we use linear mixed models and a range of other models to make sure that they're robust. And so I always will present the results from the seasonal model and the photoperiod, which is the linear model. And just as a side note, we also tested if the EEG was fine in terms of accuracy and compared it to a clinical device. And it's in preliminary analysis, it seems quite good. So we are certain that it measures the sleep stages. And now if we look at our final sample, we ended up with 10 participants, 80% of them were female and healthy students. Not just students, sorry, healthy. I mean, some of them were students, but not all of them. So some were also already starting work. And yeah, this is basically normal BMI range. This matches our selection criteria, and we have also filtered for extreme chronotypes, so they're sort of in the mid-range, and the sleep quality index was good. Yeah, and just to mention here, the photo period between summer and winter was about a 7.7 hours difference. So quite, this site was at Munich, so quite a difference here. So in the next slides, I'm going to walk you through the different EG variables that we measured, and that was total sleep time, the wake after sleep onset, sleep maintenance efficiency, the latency to the N3 stage, the first N3 stage, and to rapid eye movement. Right, so let me start with total sleep time. So we saw that monthly EG total sleep time was 27 minutes shorter in June compared to December. And why do I say June and December? Because that's when the summer solstice and winter solstice take place. So this is the biggest difference we see in photo period. And the next slides are always the same. So on the left side, we see the model outputs from the categorical seasons. And then on the right side, we see the linear models. So basically, we saw some differences here in the categories, in the seasons. But I think what I would rely more on is the change that we see in the linear model, photo period model. And yeah, it was 27 minutes shorter. This is always reported here on the titles. And I'm showing here also the individuals. So every number here is an individual, because I want you to understand that there's still quite a lot of variance. When we talk about wake after sleep onset, we saw also that it was shorter or less in the summer. So here we see some significant differences in the categories, but importantly, in the linear model, this was also true. And if you calculate it, it's around 21 minutes. And again, yeah, you see the variance, especially in this ID. When we talk about sleep maintenance efficiency, this was also higher in June compared to December. Again, significant in some of the, or actually in all of the seasons, but also in the photo period model. And here again, the individual differences. Now, when we talk about the latency, we saw that N3 was reached faster by about 34 minutes in summer. And this was true for spring and summer in the seasons, in the seasonal model, but not for autumn. And the linear model showed this quite clearly, though. Yeah. And then lastly, we also see a reduction in, something that I want to mention here is that there's a study from Van Dongen that calculated this as well. It's one of the only studies that did something similar to us in terms of study design. So there's really not many studies out there that look at this also in a high resolution manner. And they found that slow wave sleep onset was about 45 minutes earlier in summer. So it goes in the same direction and also roughly the same magnitude, which I found quite interesting. Right, and then what about REM latency? So here we also saw that it was reached faster. So REM was reached faster by about 33 minutes in June versus December, though not all of the categories were significant here in this model, but the linear model showed it again. Right, so these were the sleep architectural results. And now I just want to briefly mention some of the questionnaire results that are the monthly subjective questionnaires that we asked. And here we also saw that sleep duration was shorter. So this is a nice addition to the EEG result. I mean, obviously different numbers, but it goes in the same direction. So yeah, both the categorical model and the photo period model showed this, which is visualized here. And in this case, I also looked at the chronotype. So I wanted to see if there's an interaction with sleep duration and chronotype. And this is not something that we saw in this in these questionnaire results. But when we look at yeah, maybe first highlight here that some other studies have also looked at this from subjective data. which goes in the same direction of magnitude, so ranging between 24 to 30 minutes. And as I said earlier in our data set, it was the 27 minutes. So it's all in a similar direction. Right, and then when we talk about the sleep quality, there we don't see any difference across the year, but we do see the well-known association with chronotype. So later mid-sleep or later chronotype is basically associated with worse sleep quality in our study here as well. And this is, mid-sleep on work days and 3 days. So to sum up, this questionnaire data, we can see that, there was basically a longer sleep duration in winter, whereas in spring and summer it was reduced in both types of models, but there was no chronotype association, and for the PSQI was the difference. So no association here, but this association with chronotype. And some other questionnaires that I haven't shown you the data because there nothing came out was that there was no difference in sleepiness across the year, no difference in insomnia severity, though with this one, and also the fatigue severity scale, I want to highlight that, of course, we had a healthy population, so there were some ceiling effects, and it wasn't to be expected that there would show much difference between the seasons. But still, I wanted to collect it to make sure, first of all, that we are not reaching into sort of clinical levels, and also maybe if there was some variance, if we could see it. I also collected data from with the chroma sleep disturbances and the chroma sleep related impairments. And here we see the same thing, that there isn't any association with season or photoperiod. But I also had some perceived stress questionnaire, the PSS-10. And while the model isn't really super strong in terms of a probability, there is some tendency that there's lower stress with longer daylight duration. Yeah. Okay, so to sum this part up, what are the key findings then? So during summer months, we see that participants slept shorter, about 25 minutes. They reached REM and non-REM phases quicker by about 17 to 33 minutes. They spent less time awake, about 21 minutes less. They had 3.1% better sleep maintenance. They tended, I didn't show you this, but they also tended to have earlier chronotypes in the summer months. And also something I didn't show you was that their body weight was reduced by about 1.4 kilos, also something that we know from the literature. And the light exposure was more. And I haven't shown you the data here because, especially with the light exposure, I will go to this. I think we need to analyze this quite deeply to understand what's happening. Because is it just the light exposure that we get more during the summer because of photoperiod, or does our behavior change? And this is something I really want to investigate deeper. That's why I didn't want to show you too much here right now, because I've just finished the data collection a couple of months ago, so it's quite preliminary data. But still, what's interesting here is then, I think, to ask the question, well, what about the summer sleep? Is this more consolidated and efficient? Or does it actually show sleep deprivation and earlier circadian phase? And that's why I think we really need to go into this light analysis to make sure what's going on here, and also to go a bit deeper into some of the EEG variables that we have, and see if slow wave sleep power, for example, changed. But still, also interesting is that most variance in these variables is really explained by within participant variation. So in the end, I think it highlights the importance of these individual approaches that I talked about at the beginning. So right, in the last couple of minutes, I just want to present to you where I think we can be heading towards personalized prevention and how we could do this. So I think in the first step, we need to understand what's going on, right? So maybe come up with individualized behaviors and profiles. And this is something I show you here on this slide. So if we imagine that we have individual 1 and individual 2, they might have some overlaps in what they're doing, but largely they are quite different. And they show some behaviors with light. And obviously, I mean, you can translate this to sleep behavior as well. I'm just focusing here on the light part. And then you wanna with the individual together find out what are the target behaviors that we want to change and what are these barriers. So for this individual here, they can't change anything about the lighting situation at work, for example, but they can do something about when they do their walks, their daily walks. Whereas this person, they are working shift work, so they cannot change this unless they want to change jobs, or it's very limited choice they have here, but they can reduce the video gaming at night. And then in a third step, you can come up with some behavior change interventions. There are different ideas on how to do this, of course, and different elements to this, but it could include a circadian health education part. It could, as we said here, identify the target behavior, help individuals by using smart implementation techniques. And also, I think most importantly, especially for long-term change, we need to change habits. So, integrate this in your daily routines. And how are we going to deliver this? So I think there are some options using technology, of course. This is not exclusive or exhaustive. I mean, there's other ways of how we can deliver this. One idea is to have some effective, simple, tailored, accessible interventions using mobile phones, for example, or also adaptive and just-in-time interventions. And these could even include like weather information. So let's say, okay, you get this information, today's a sunny day. Don't you want to go outside and enjoy your lunch break outside, for example? And it could also make use of all these loggers and variables that we now developing or already out that are already out there to passively or actively log your behavior and light exposure. And of course, also collect all these other contextual factors that we know independently might influence sleep and light exposure, but together we haven't really figured this out because it's so complex. So if we collect some data here, maybe we will eventually get there to put this into a more holistic point. Yeah, and with this, I already want to end, but there's one more slide that is quite important to me. And so, we've developed a book about light, which is called Lumis Delight. It's a comic book for children, age 6 to 10, but I think if you're an adult, you might also enjoy it. So it's a PDF currently in English, German, and French, but there will be more languages. So please just go to the website or use the QR code here. And it's free, just download it, share it with your children, with your partners, colleagues. Anything would help to distribute it. And with this, I wanna end my talk. Thank everyone, thank you. And of course the group for all the support and the funders. Thank you very much.